Welcome to the sixth session of this differentiation series. Building up from the skills learned from previous sessions, we will explore the techniques to establish tangent line equations, particularly to find the derivatives of composite functions as well as implicit functions. We will demonstrate 8 worked examples in this session.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to the series of differentiation, and this is the 6th session of this series. Here, example 1 is to find an equation of the tangent line to the graph of f of x at the point 1, -4. Since f of x equals the product of x cubed plus 4x minus 1, all in parentheses, and x minus 2, all in parentheses, the differentiation product rule is used to find its derivative. Hence, f prime of x equals the derivative of x cubed plus 4x minus 1, all in parentheses, times x minus 2, all in parentheses, plus x cubed plus 4x minus 1, all in parentheses, times the derivative of x minus 2, all in parentheses, which equals 3x squared plus 4, all in parentheses, times x minus 2, all in parentheses, plus x cubed plus 4x minus 1, all in parentheses, times 1. After being further expanded and simplified, f prime of x equals 4x cubed minus 6x squared plus 8x minus 9. Hence, f prime of 1 equals -3. Accordingly, the line equation is written to y minus -4 equals -3 times x minus 1, all in parentheses, which is simplified to y equals -3x minus 1. The question in example 2 is to find the derivative of the composite function y equals f of natural logarithm of open bracket x plus square root of a plus x squared close bracket, where function f is differentiable. Since it involves the composite function, chain rule must be used to find its derivative. So y prime equals f prime of natural logarithm of open bracket x plus square root of a plus x squared close bracket times 1 over the sum of x and the square root of a plus x squared times the derivative of x plus square root of a plus x squared, all in parentheses, which can be simplified to f prime of natural logarithm of open bracket x plus square root of a plus x squared close bracket times the ratio of 1 plus x over the square root of a plus x squared, all to the sum of x and the square root of a plus x squared. After being further simplified, y prime equals f prime of natural logarithm of open bracket x plus square root of a plus x squared close bracket times the reciprocal of square root of a plus x squared. Up to this point, most functions have been expressed in explicit form. The variable y is explicitly written as a function of x. Since not all the functions can be expressed explicitly, we need to learn how to use the implicit differentiation method to find its derivative function. Here are the guidelines for implicit differentiation, and it has 4 steps to find dy by dx. The first step is to differentiate both sides of the equation with respect to x. The following step is to collect all the terms involving dy by dx on the left side of the equation and move all the other terms to the right side of the equation. Step 3 is to factor dy by dx out of the left side of the equation, and the last step is to find the expression of dy by dx. Example 3 is to determine the slope of the tangent line to the graph of x squared plus 4y squared equals 4 at the point square root 2 negative 1 over square root 2. To find its derivative, we follow the above guidelines and to differentiate both sides of the equation with respect to x first. Accordingly, dx squared plus 4y squared, or in parentheses with respect to x, equals d4 by dx, which is written to 2x plus 8y times dy by dx equals 0. Hence, dy by dx equals negative x over 4y, which equals 1 over 2 when x equals square root 2 and y equals negative 1 over square root 2. Example 4 is to find y prime, given that y cubed plus y squared minus 5y minus x squared equals negative 4. Following the guidelines, we differentiate both sides of the equation with respect to x, so the differentiation of y cubed plus y squared minus 5y minus x squared with respect to x equals the differentiation of negative 4 with respect to x, which equals 0. Hence, dy cubed by dx plus dy squared by dx minus d5y by dx minus dx squared by dx equals 0. After finding the derivatives of each term, we have 3y squared times dy by dx plus 2y times dy by dx minus 5 times dy by dx minus 2x equals 0. Hence, the term with dy by dx are kept on the left side of the equation, while the term 2x is moved to the right side of the equation. Then dy by dx is the common factor of all the terms on the left side, and after being factored, the equation becomes dy by dx times 3y squared plus 2y minus 5, or in parentheses equals 2x. Therefore, dy by dx equals 2x over the result of 3y squared plus 2y minus 5. Example 5 is to evaluate the derivative dy by dx as well as its second derivative of y with respect to x at the point negative 3, 4. Given that x squared plus y squared equals 25. Based on the given function x squared plus y squared equals 25, we differentiate each term with respect to x. So d dx of x squared plus y squared equals d dx of 25, which can be written to 2x plus 2y times dy by dx equals 0. Hence, dy by dx equals negative x over y, which equals 3 over 4 at the point x equals negative 3 and y equals 4. Now, based on the first derivative, we find the second derivative d squared y over dx squared equals negative of y minus x times y prime all over y squared, which equals negative y minus x times negative x over y all over y squared, which is simplified to negative of y squared plus x squared all over y cubed, which is negative 25 over y cubed. Hence, the second derivative d squared y over dx squared equals negative 25 over 64 at the point x equals negative 3 and y equals 4. Example 6 is to find the slope of the graph. 3 times x squared plus y squared, or in parentheses squared, equals 100xy at the point 3, 1. Based on the given function, we differentiate both sides of the equation with respect to x. So dx of 3 times x squared plus y squared, or in parentheses squared, equals dx of 100xy. Hence 3 times x squared plus y squared, or in parentheses times dx squared by dx plus dy squared by dx, or in parentheses equals 100 times dx by dx times y plus dy by dx times x, or in parentheses. After working out the derivatives, it becomes 6 times x squared plus y squared, or in parentheses times 2x plus 2y times dy by dx, or in parentheses, equals 100 times y plus x times dy by dx, or in parentheses. After expanding the brackets and moving the terms with dy by dx to the left side of the equation, while moving the terms without dy by dx to the right side of the equation, dy by dx is factored out, which equals the ratio of 25y minus 3x times x squared plus y squared, or in parentheses, or to the result of 3y times x squared plus y squared, or in parentheses minus 25x, which equals 13/9, after substituting x by 3, y by 1, respectively. In example 7, the question is to find the derivative of f of x, which equals the product of x and the modulus of x. It also asks if the second derivative of this function exists at the point x equals 0. Since the function of x times its modulus is written to x squared when x is greater than 0, it equals 0 when x equals 0, and it equals negative x squared when x is less than 0. Hence, its derivative function equals 2x when x is greater than 0. It equals 0 when x is 0. It equals negative 2x when x is less than 0. In summary, the derivative of f of x can be simplified to 2 times the modulus of x. As for the second derivative of f of x, it equals 2 when x is greater than 0. It equals negative 2 when x is less than 0. Since the right-hand second derivative equals the limit of f prime of 0 plus x minus f prime of 0 all over x as x approaches from the right of 0, which is 2. However, the left-hand second derivative equals the limit of f prime of 0 plus x minus f prime of 0 all over x as x approaches from the left of 0, which is negative 2. Since the right-hand second derivative does not equal to the left-hand second derivative at the point x equals 0, the second derivative of f of x does not exist at the point x equals 0. The question in example 8 is to find the tangent line at the point square root 2 over 2, square root 2 over 2. The function is shown in its implicit form, x squared times the sum of x squared and y squared, that equals y squared. We start to expand the left side of the equation and then differentiate each term on both sides of the equation with respect to x. Hence, ddx of x raised to the 4th plus x squared y squared, or in parentheses equals ddx of y squared. After differentiation, it becomes 4x cubed plus x squared times the derivative of y squared plus the derivative of x squared times y squared equals 2y times y prime. After further differentiation and then rearranging the terms by moving the terms with y prime on the left side of the equation and the terms without y prime to the right side of the equation, then we have the expression of y prime, which equals 2x cubed plus x times y squared all over y times 1 minus x squared all in parentheses. Finally, it equals 3 when substituting both x and y by square root 2 over 2. Hence the line equation is written to y minus square root 2 over 2 equals 3 times x minus square root 2 over 2. After being simplified, it becomes y equals 3x minus square root 2. If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.